Hello, my name is David Ortiz. I am from Kingsville, Texas, and I will be graduating in May 2026 with my bachelor's in electrical engineering. I will be presenting my project design and implementation of a solar battery charging system using NPPT. So the reason I wrote on this topic is to explain how a solar charging system that uses maximum power point tracking, or MPPT, can be used to increase charging efficiency and possibly be implemented into the university system. First, I'll introduce the background of the problem and why MPPT is important. Then I'll explain what MPPT is and summarize relevant research. Next, I'll walk through the design of my system. After that, I'll present experimental results and compare MPPT to PWM charging. Finally, I'll conclude with recommendations for future work as well. So here, solar panels are an excellent renewable energy source, but one major issue is that their output constantly changes. Temperature, shading, and sunlight intensity all affect how much power a panel can produce. Because of this, solar panels rarely operate at their own maximum power. This is where MPPT comes in. Its job is to find and maintain the best possible operating point so more energy can be harvested efficiently. The motivation for this project came from the mere fact that many small solar systems, especially low-cost or DIY systems, rely on simple PWM charge controllers. PWM controllers are easy to use, but they're not very efficient. They leave a lot of solar power unused. I wanted a system that improves efficiency without requiring expensive commercial MPPT hardware. So this led to many hours of research for articles about testing around an Arduino implementing the MPPT algorithm. So that way we can basically use this for free charging stations around campus, inside and out. The objective of this project was straightforward. First, to design and build a low-cost MPPT solar charging system. Second, to implement an incremental conductance, or INC, algorithm on an Arduino. Third, I wanted to integrate the MPPT logic with a buck converter to properly charge a 12-volt battery. And finally, to test the system under different lighting conditions and compare its efficiency to a PWM reference. So, what is MPPT? MPPT stands for Maximum Power Point Tracking. When light changes, the solar panel's optimal voltage and current also change. MPPT continuously adjusts the system so the panel operates exactly at the point where it produces the most power. It does this by controlling the duty cycle of the DC-DC converter. So in simple terms, MPPT acts like an automatic optimizer that squeezes the most energy possible from the solar panel. So why would we want to use MPPT? Without MPPT, the system is basically guessing how much power it can take from the panel. This leads to lower current, unstable voltage, and overall wasted solar energy. MPPT solves this by actively searching for the maximum power point and adjusting in real time. As a result, systems using MPPT typically gain 20 to 30% more usable energy compared to PWM. This project demonstrates that improvement directly. Here's a conceptual overview of the incremental conductance algorithm, or INC algorithm. At the maximum power point, the derivative of power with respect to voltage is 0. INC uses this relationship by comparing the ratio of change in current and change in voltage. If the system is to the left or right of the maximum point, the algorithm adjusts the duty cycle until the correct point is reached. This method is more stable and has less oscillations compared to simpler approaches like perturb and observe. This design is supported by findings from several researchers, such as we have Bahadu and Mondal. They demonstrated that Arduino-based MPPT is both low cost and effective. We have Oho and Ogunlowo show that MPPT consistently outperforms PWM systems by a negotiable margin. We also have Potter and colleagues compared multiple tracking algorithms and concluded that incremental conductance is one of the most accurate and stable. This research helped validate my decision to use the INC algorithm. So all of my research sources are also listed at the end of my presentation. This slide shows the overall flow of the system. So we have the solar panel that feeds energy into the sensors, which measure voltage and current. These readings go to the Arduino running the MPPT algorithm. The Arduino then sends control signals to the buck converter, adjusting its duty cycle. Finally, the converter charges the battery using the optimized power from the panel. These are the main components used in the system. We have a 20-watt solar panel that provides the input. An Arduino Uno acts as the controller. The buck converter is built around an IRF Z44N MOSFET, a Schottky diode, a 220 microhenry inductor, and a 470 microfarad capacitor. This system charges a 12-volt lead-acid battery. Each component contributes to a balancing cost, availability, and performance. So here is a summary of how the MPPT algorithm operation runs. So the system repeatedly measures the voltage and current. It then calculates the change in both values, then determines whether it is operating above or below the maximum power point. Based on that comparison, the duty cycle of the buck converter is increased or decreased. This loop runs continuously, allowing the system to respond instantly to changes in sunlight. So to test the system, researchers performed measurements outdoors under 3 conditions. We have full sunlight, partial shading, and cloudy weather. A PWM controller was used as the reference baseline. Researchers monitored the changing current, voltage levels, and efficiency throughout the test. The goal of this was to determine how effectively MPPT improved the charging performance compared to PWM. So here are the main findings of that research, or of those testing conditions. So under all the conditions, the MPPT controller delivered higher and more stable voltage and current. The response time to shading or cloud movement was less than 1 second, which is about 50% better than most solar systems in America. Overall, the MPPT system improved energy capture by about 27% compared to the PWM reference. Next, we have this slide that summarizes the numerical results. In sunlight, MPPT reached over 95% efficiency compared to the 76% with PWM. Even under partial shade and cloudy conditions, MPPT maintained above 89% efficiency. PWM consistently underperformed and showed more unstable behavior. This data clearly demonstrates the benefits of MPPT versus PWM. So, in conclusion, this project successfully met all of its objectives. The incremental conductance algorithm proved to be accurate, responsive, and stable. The system significantly increased charging efficiency while remaining affordable and easy to build. Overall, this MPPT design is well suited for educational purposes and small renewable energy applications. So for future improvements, I recommend adding IoT monitoring so the system can send real-time performance. This will help when charging outside if something is malfunctioning or not working correctly. It can communicate to the IT department and let them know that something is going wrong, so that way we can get any problems or glitches fixed and ready to go again, so that way they can be continue to be used as charging stations. They can also explore AI-based MPPT algorithms like neural networks, which could further improve the accuracy. More precise sensors would also help track performance under rapidly changing conditions. I know a lot of times here in South Texas, the weather is very unpredictable, so this will be able to help a lot, possibly even adding some umbrellas over the charging stations that will be placed outside. Could also help if a student is stuck in the rain, then they can sit there and charge their phone or laptop or whatever device they have, so that way they can either join a Zoom for class or do any like attendance assignment that is required for that class. Finally, I have scaling the design to handle larger solar panels, which will make it suitable for bigger installations, which we can possibly expand this to, instead of just charging stations, we can use it for powering possibly different buildings at the university. Um, that is the end of my presentation. Thank you very much, and here are my references.